G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening. If it's cold, I hope you're having a hot chocolate or a coffee. If it's hot, hopefully you're getting a cool drink with some ice. Anyway, I pray God's blessing you. Okay, this is lecture 10. So we're going to do topological space, the topology of R, which is the reals, interior and exterior, boundary and neighborhoods. There's a few little things that break up in the middle of all of that. What I've done in this lecture is try to give a lot of examples, so hopefully that'll help you with your study. And there's also, I've made up a whole bunch of questions at the end. So let's go. So topological space. Topological space is defined in terms of open sets. You could define it in terms of closed sets, but it's typically defined in terms of open sets. So a great article to help you understand this is on Stack Exchange. It's actually a discussion that they're having about it. I really encourage you to read that. It's really good just to help your mind understand about open and closed sets. Definition. A topological space is a set of points combined with a collection of its subsets called open sets, which satisfy the following axioms. The empty set is open. The entire set is open. The union of any number of open sets is open, and the intersection of a finite number of open sets is also open. So that's a topological space. So a variation, I'll just move me out of the way. A variation on the above definition using set X and subsets T can be found in Wolfram Math World. So I've given the link there. This includes a variation that defines the whole lot in terms of closed sets. So where I've got set X and subsets T, here in the definition, what they've said is topological space is a set X consisting of a collection of its subsets T, and it's using X and T, so that might help you, or might be better for you in understanding, well, that's T, that X belongs to that T, etc., etc. So it's still saying the same thing, but again, just a different way of expressing it that might help you. So anyway, two things there that I think would be helpful for you to look through. Topology of R. So R is the real space. So the topology of R is created by open intervals. Again, he's using open. The set of all open intervals forms a base or a basis for the topology, meaning that every open set is a union of some collection of sets. So the topology of real numbers can be open, closed, connected, or disconnected, or can be combinations of those things. Obviously, it can't be open and, or actually it can be open. So these are things which define or help define the way sets are looked at. Again, here's another link for you to look at. So this is in LibreText. LibreText are pretty good online text. Okay, just looking at open. A set U is called an open set if for every X belonging to U, there exists a bounded open interval, A, B, containing X such that A and B are subsets of U. So if U and V are open sets, then U union V is an open set, and U intersection V is also an open set. So once you've got an open set, it pretty much keeps everything open. And here's some examples. I think I'm going to have to move this up here because I think they go for a fair way across the screen. They do, look at that. Okay, 0, 1 with the rounded brackets is the set of all real numbers from 0 to 1, but not including the endpoints. 0 and 1 are not included. So that's the rounded brackets. All real, the set of all reals, this is considered an open set. 0, 1, union with 3, 4, again with the rounded brackets, is open since it's the union of open sets. The complement of a closed set is always open. Obviously, if it's closed, the opposite of that is open, and vice versa. The empty set is both open and closed, so it's going to appear when we have closed up the top. An open disk in 2D planes, such as x squared plus y squared is less than 1, that's regarded as open because it's not including the boundary, which is the circle. An open ball, for example, where x is element of the reals, x minus 5 is less than 2. So this equates to the open interval from 3 to 7, not including 3 or 7. Okay, so there's some examples of open sets. Closed. So let's have a look at closed. We'll be down here for the moment. A set U which is a subset of the reals, is called closed if a closed set if U contains all of its limit points, which is pretty obvious. We've seen that before, and we've seen, sure seen most of this before. I think it's in lecture 2, in lecture 3 or 4. If U and V are closed, then U union V may be open or closed, but U intersection V is definitely a closed set. For example, so again, I have to move me up here. 0, 1, square brackets around it, is the set of all real numbers from 0 to 1. The endpoints 0 and 1 are included. Any single point, for example, 2, it could be any number you want, is a closed set because it only includes the point. 0, 1 union with 3, 4 is closed since it's the union of two closed intervals. The complement of an open set is a closed set. Well, that's pretty obvious from before. Complement of a closed set is an open set, etc., etc. The empty set is both open and closed, as I said previously. A closed disk in 2D plans such as x squared plus y squared less than or equal to 1 is closed, so that includes the boundary of the actual circle. A closed ball, for example, x being an element of R, where x minus 5 is less than or equal to 2, and this equates to the closed interval from 3 to 7, including both 3 and 7. So there's some examples of closed sets. So now we're going to look at connected sets. Okay, connected set is a set that cannot be partitioned into two non-empty open subsets in the relative topology induced on the set. So I'll just say that again. A connected set is a set that cannot be partitioned into two non-empty open subsets in whatever topology you're looking at. So examples of connected: any closed interval, for example, 0, 1, which is closed, that is a connected set. You can't split that up. In other words, what you're trying to do is you're trying to find a point at which you can say from this point onwards it splits, where you can't split up a closed interval. You can't split up an open interval either. You can't find a point from which you can go to and then continue on from the next point afterwards. I'll give you an example. Let's go from 0 to a half. Well, what are you going to go to? If you're going from here, you're going to go from 0 to a half. What's the next point? Well, I don't know. What is the next thing after a half? You can't actually find that next point to label it and say, well, I'm going from the half and continue onwards. So you can't actually split it. So it's regarded as a connected set. You can't partition it really easily. Any set of points on a straight line, well, you can't partition that. The set of all real numbers, again, you can't partition where one real number finishes and find the next real number. The set of the entire complex plane, you can't split up the complex plane, similar to the real numbers. A sine curve can't be split up. Any set of constant functions, they cannot be split up. Any convex set in Rn, including polygons, that cannot be split up. An open or closed disk, that can't be split up. And that's it. So there's our different bunch of sets as examples of connected sets. They can't be partitioned into two open subsets. Okay, that's it. You can't partition into two open subsets because if you have an open subset, let's say it ends at a half and then starts at a half, where's the half? Because if it's both open on each end, it doesn't work. So disconnected. A disconnected set is a set that can be partitioned into two non-empty open subsets. Again, we've got this open. It can be partitioned. So this can be partitioned. For example, 2-point set, e.g. 1 and 2. So you can split that really easy. There's 1, there's 2. We can partition that. The set of rational numbers, we can partition that. The set of real numbers minus a single point. So if you take out a single point, let's take out 2, then we can make two open subsets going up to 2, but not including 2. And then we've got disconnection. The set of integers, we can split that easily because they are individual points. A finite set of points, e.g. 1, 2, 3, 4. That's easy to split up. You can split up into 1, and then 2, 3, 4. The Cantor set. So if you're not aware of the Cantor set, you could Google it if you want. Cantor set's really interesting. It's removing the center third. So if you've got a set and you keep removing the center, you remove the center third, then you've got the first third and the third third, and that's your new set. then you remove the center third of that. So a Cantor set is a continuous loop of removing the center third. It's really interesting. You might want to look that up. Any disconnected graph is obviously that's because it's disconnected at a certain point, so that can be split up. A set of non-zero constant functions, for example, fx equals 4 and fx equals 5. So they're constant functions. That's always 4 and that's always 5. So we can split that up. A set of, image in the way, a set of bounded sequences that can be separated from unbounded sequences. So that's pretty easy as well. So these are examples of disconnected sets. Interior and exterior. So the next thing we want to look at is the interior of a set can be defined as the largest open set contained within it. And this is pretty obvious once we do some examples here. So examples. The interior of the closed interval 1, 2, so it includes 1 and 2, is the open interval 1, 2. So the open interval 1, 2 is included inside 1, 2 in this closed interval, and it's regarded as the interior because it includes everything except for these two endpoints. The interior of a sphere is the open ball without the boundary. The interior of a square that does not include the boundary. Okay, so they're just examples of the interior of a set, the largest open set contained within it. The exterior of a set can be defined as all points in the neighborhood that are disjoint from the set. So basically you're looking at what is outside. Really easy examples now. The exterior of the closed interval 1, 2, so this is closed, is the union of the open intervals minus infinity up to 1, but not including 1, union with not including 1 up to infinity. So that's the exterior of that closed interval. It's the union of the open intervals. The exterior of a circle is all points outside the circle. So for example, here we've got x squared plus y squared is greater than 2, assuming the circle finishes at 2, then it's the rest of the area. So if you're doing that on a diagram, you'd be drawing a circle and then coloring in everything outside of the circle. With dots, you do this with dots, obviously, a dotted circle. The exterior of the set of even numbers is the set of odd numbers. There you go. Pretty easy to understand that. Boundary. Now, I've done boundaries before. What we're doing here in this lecture is we're just expanding on things that we've done before in the majority of instances. The boundary of a set A is defined as all points x, that's all the points x that set the topological boundary. It consists of all points x such that every neighborhood of x intersects both A and AC. And I've written there A complement, just in case you're unsure of what AC is. Examples. The endpoints of a set's interval. So this includes both open and closed sets. For example, 0 and 1 are boundary points. So look at boundary points of both the open set 0, 1 and the closed set 0, 1. So 0 and 1 are the boundary points of both the open set and the closed set. The set of integers is the boundary. Now, this is really interesting. The set of integers is the boundary of the set of integers. So I'll just read that again. The set of integers is the boundary of the set of integers. And I've written an explanation here. So the whole set is the boundary of the set itself. This is because each element is an isolated point. So notice here that minus infinity and infinity are not the boundary. You don't say what is the boundary of the integers. You can't say it goes from minus infinity to infinity. They're the boundary. That's not true. The set of integers is the boundary of the set of integers. Very rare, but it applies to them. In comparison, the boundary of the set of all points in a circle is actually the circle itself. So the boundary of the points inside the circle is the circle. And here we go with these three. You'll like these three. The boundary of real numbers is the empty set. And the boundary of complex numbers is the empty set. And check this last one out. The boundary of the empty set is the empty set. Gotta love that one. So here we go. So the set of integers is the boundary of the set of integers, but the boundary of real, complex, and the empty set is, in each case, the empty set. So there's food for thought. You can think on those things, but they're all very interesting. So they're boundaries. And it's based on, if you look at the definition and think about it, it makes a bit of sense. Neighborhoods. Now, we've done neighborhoods before, and again, this is revision and expanding on it. Neighborhoods are defined as an open set which surrounds a point within a set. So a set U is a neighborhood of the set S if it is a neighborhood of every point in S. And this will give you a clearer understanding of a neighborhood, because I'll give you some pretty good, or what I think are pretty good examples. So neighborhood exists on boundary of open sets, but they do not exist on the boundary of closed sets. Well, that's pretty obvious. We've done that before. So let S be the open interval 1, 2. So we're not including 1 or 2. Then the larger open interval P, 0, 3, which contains S, so this smaller interval here from 1 to 2, not including 1 and 2, is inside 0 to 3, not including 0 to 3. So that contains S and is open. That is a neighborhood of S. So the larger interval is a neighborhood of the smaller interval. Okay, the larger interval is a neighborhood of the smaller interval. Try and remember that. That's a pretty good sentence to remember. So here we go. Again, let M, and I've just used different letters here, let M be the open interval 1, 2, and N be the closed interval 1, 2. So this includes 1, 2. Then N is a neighborhood of M. In other words, the larger one, which is 1, 2, including the boundary, is a neighborhood of M. Since N contains the open interval M, even though N is in itself closed. Okay? So the larger interval is the neighborhood of the smaller interval, not the other way around. That's it. That's all I've got for week 10. And I've put in a bunch of questions here to sort of make you revise those things and write out sentences. Obviously, there's answers there. And here we go. How is connectedness defined in topological space? Is a topological space with a discrete topology compact? What is the usual topology of real numbers? What does it mean for a function to be continuous in terms of real numbers? Explain the difference between open and closed sets. List 3 clopen sets, i.e. sets that can be open or closed. And are the following sets open, closed, connected, disconnected? And there might be a few of those things. Okay, that's it. God bless you. I'll see you next week. Then we'll have more information and more questions. Week 11 is going to be the last week of new information. And there's a lot in week 11 because I've moved a lot of the week 12 stuff into week 11. So almost certainly there'll be 2 videos. God bless you. Stay safe. Keep studying. And yeah, all the best. Okay, bye.